Oh, he has a YouTube channel. Oh, that's cute. Oh, he's trying.
Mr. Nicely, you're muted.
Okay, can you guys out there in Zoom hear me now?
Yes, sir.
Okay. Let's see here. Okay, so before I begin, I don't think I need to say much in addition to the announcement I made over the weekend. Just to remind you that the deadline for submission of your do-over, so to speak, for test number 1, if you so choose to do it, and I can't imagine any reason why most of you won't do it, given the class average. It's due tomorrow, so make sure you submit it so that I can get it and grade it in time to send it back to you. All right? Okay, so with that said, let's try to finish up on this chapter. And what we'll be looking at here are the different acid-base properties displayed by salts. Now, I know when I taught Chem 1, Miss Miller was in my class. I don't think anybody else was in my class. I remember talking about the neutralization reaction, right? Which is basically an acid reacting with a base to form a salt and water, right? And I think I remember saying that basically in this reaction, the whole idea behind the neutralization reaction is that you have something acidic reacting with something basic, and the resulting products would be neutral, right? The water is definitely neutral, and one would presume that the salt would be neutral as well, right? So just to give a simple example, if you take sodium chloride and react it with sodium hydroxide, I'm sorry, if you take hydrochloric acid and react it with sodium hydroxide, right? This is the acid, this is the base, and we can figure out what the salt is. We simply take the positive part of the acid, of the base, and combine it with the negative part of the acid, and you're going to get the formula for the salt, which in this case would be sodium chloride and water, right? Now we know that water is neutral, right? The sodium chloride in this particular case would be neutral as well, all right? So this is basically why we call this the neutralization reaction, right? Presumably, the products of the reaction between something which is acidic and something which is basic would be neutral. Now, in truth and in fact, this is not always going to be the case. And I think I've made mention of that fact whenever I teach General Chemistry 1. And here we're going to see why that is not the case in all situations of an acid reacting with a base. What you'll find is that the acidic or basic properties of salts would be largely a function of how strong an acid and or base are involved in its creation, all right? So we're going to talk about the three different types of salts with respect to acid-base properties. We have neutral salts, where basically any salt containing an alkali metal or alkaline earth metal, with the exception of beryllium, and the conjugate base of a strong acid, such as the examples you see here, chloride, bromide, and nitrate, those salts will be neutral, right? So basically, a salt consisting of a group 1A or group 2A metal, with the exception of beryllium, along with the conjugate base of strong acids. And remember, you guys should know what the 6 strong acids are, all right? I won't go through that again, right? But you need to remember the 6 strong acids. If you have conjugate bases of those acids in combination with group 1A or group 2A metals, with the exception of beryllium, then those salts will be neutral, all right? So for example, sodium chloride is one such example, the one that we just saw, I just mentioned. The sodium is from group 1A, and the chloride is the conjugate base of a strong acid. So basically, the sodium and chloride ions are very stable, and therefore will not in any way react with the water to form an acidic or basic solution, all right? Now, in the case of basic solution, these are formed from salts derived from a strong base and a weak acid, right? So basically, the salt is coming from a strong base and a weak acid reacting to form a salt and water. Basically, you're going to end up with a basic solution. So for example, and this is not totally correct, this hydrogen should not be here. So please make a note of this, right? This hydrogen here should not be here, all right? It should simply be NaCH3COO, all right? So this is basically a salt formed from a strong base, which would be sodium hydroxide, and a weak acid, which would be acetic acid. And when this dissolves in water, it dissociates, completely dissociates to form these ions. Now, the thing about the sodium, as we said before, as in the case here, the sodium will not react with water to cause any change in the pH. However, the acetate ion is a strong enough base such that it can react with water to produce the hydroxide ion, right? And as a result of that, the resulting solution will be basic, all right? So the sodium acetate would be considered to be a basic salt because the acetate that is formed upon dissociation will react with water to form hydroxide ions, and therefore the resulting solution will be basic. All right, then we have acidic salts, and these are salts that are derived from a strong acid and a weak base, all right? An example of this would be ammonium chloride. When ammonium chloride is added to water, well, firstly, ammonium chloride is formed from a weak base, which would be ammonia, and a strong acid, which is hydrochloric acid. So when the ammonium chloride dissociates, as in the case of all ionic compounds, when they're added to water, it forms the ammonium ion and the chloride ion. Now, the thing is, the chloride ion is a very weak conjugate base, as we said before, and therefore will not interact with water because it's very stable. The ammonium ion, on the other hand, will react so as to release hydrogen ions, as you can see here from this equation, right? And therefore, as a result of the constant of the hydronium ions or the hydrogen ions being produced in this reaction, the resulting solution is going to be acidic, all right? And then we have a situation where acid solutions will be formed if you have a salt where the metal ion is very small and highly charged, right? We say in chemistry, we say that they have a high charge density, all right? So examples include aluminum, chromium, and the beryllium ion. Basically, if you have those ions in combination with the conjugate base of a strong acid, then what will happen is that the ion itself will undergo hydrolysis to form an acid solution. So in the case of the aluminum ion, what happens is that initially the aluminum ion will form this complex ion where you have the aluminum in the center surrounded by 6 water molecules in an octahedral fashion. You're going to see how that looks like in the next slide. And what happens is this reaction here, where a hydrogen ion is released, and the result will be the formation of this structure here. But by virtue of the fact that you have hydrogen ions being produced here, the resulting solution will be acidic, all right? So that's what happens in the case of aluminum, and you can have a similar thing happening in the case of chromium and also in the case of beryllium. So the next slide shows you basically what happens in terms of the actual structure of the complex here. So this is the aluminum here, which has water molecules bonded to it, right? And as you can see, it has an octahedral shape. And what happens is that you're going to have a situation where the aluminum, which, as we said before, is small and highly charged. This is the aluminum ion. And because it's small and highly charged, it is going to attract the electrons from the oxygen here. The result will be the attraction of electrons of from the hydrogen here to this oxygen. And this hydrogen, therefore, can be attached to this oxygen. So this oxygen is going to basically donate a pair of electrons here from a water molecule to pick up this hydrogen here to form the hydronium ion, which is formed here. And here you'll be left with this oxygen here with a negative charge shown here with one hydrogen here, and this oxygen is still bonded to the aluminum ion. So therefore, the formation of the hydronium ion is basically what results in the solution being acidic in this particular case, all right? Okay, so that's what happens in the case of a situation where you have a small positively charged ion in an aqueous solution in combination with a stable conjugate or stable anion, right? In this case, it's the aluminum ion that will result in an acidic solution, basically, according to the mechanism shown here. Okay, so this is just a summary of what we just discussed, plus one other situation which we didn't talk about. So basically, if you're asked whether or not a particular ionic compound is acidic or basic, these are the things that you have to consider. Basically, what it comes down to is the interaction between the cation and the anion, and or the anion with water to produce either hydrogen ions or hydroxide ions. So in the case of a situation where the anion has a Kb value which is greater than the Ka for the cation, then the solution will be basic, all right? If the situation is reversed, if the Kb of the anion is less than the Ka for the cation, then the solution will be acidic, all right? And then if the Kb for the anion is approximately the same as the Ka for the cation, then the solution will be neutral, all right? So that's basically a summary of how you can make a prediction as to whether or not a particular ionic compound, when added to water, will make the solution either acidic, basic, or neutral. And we kind of break down this summary here, down here, where it says, okay, so just to give you an idea as to what this table is saying, this column here determines, or it is basically where you're going to list the type of salt. Some examples are shown here. And the question is here, whether or not the ions will undergo hydrolysis and the resulting pH. So if you're dealing with a salt where the cation is from a strong base and the anion is from a strong acid, then basically none of the ions will undergo hydrolysis, which means that there's been no effect on the pH, which means that the pH of the solution will be 7. On the other hand, if the cation is from a strong base and the anion is from a weak acid, then basically the ion that will undergo hydrolysis will be the anion. If the anion undergoes hydrolysis, because the anion is a conjugate base, that means that it's going to increase the concentration of hydroxide when it's added to water, which means that the pH of the resulting solution is going to be above 7. If the cation is from a weak base and the anion is from a strong acid, then basically what will happen is that the cation will react with the water and therefore will produce hydronium ions or hydrogen ions, and the resulting solution will be acidic, which means that the pH will be less than 7. Now, if you have a situation where both the anion and the cation are formed from weak acids and bases respectively, then basically it all comes down to whether or not the Kb value is greater or less than Ka. So if the Kb is less than Ka, that means that the resulting solution is going to be acidic. If the KB is greater than KA, the resulting solution is going to be basic. And if the KB is approximately equal to KA, then the resulting solution will be approximately neutral, all right? And then the last one, which is a kind of special category, if the cation is a metal ion, which is highly charged and small, in other words, as I said before, has a high charge density, and the anion is from a strong acid, then basically the resulting solution will be acidic. In other words, the pH would be less than 7. And that's because the highly charged ion will interact with the water, as I showed you in the case of the aluminum ion, to hydrolyze it so that hydrogen ions will be produced. All right, so that's basically how you can summarize whether or not a solution of a salt will be either acidic, basic, or neutral. Okay, any questions about this? Any questions?
That table in our book.
I don't think so, but this is just an example. It's basically in the PowerPoint, which is posted online, so you can look at it. So just to give you, before we move on to the next topic, just to give you a couple of examples of how you can make such predictions. What am I doing? Okay, so let's say you're given okay, so let's say you're given potassium fluoride, right? And let's say you're asked whether or not the solution is acidic, basic, or neutral, all right? So what you'd have to do is first look at what happens when potassium fluoride is dissolved in water. It forms the potassium ion and the fluoride ion. And then you have to ask yourself, will each of these interact with water in any meaningful way, right? Well, because potassium is from group 1A, right, and can be formed from a strong base, which would be potassium hydroxide, to give you K plus and OH minus, that means that this is very weak, right? So therefore, this will not react with water at all. No reaction will take place between the potassium and the water. On the other hand, the fluoride ion is a very weak acid, or is formed from a very weak acid. So there you'd expect some interaction between the fluoride ion and the water to form HF plus OH minus. In fact, this would be a reversible situation right here. So therefore, one would expect that there will be some hydroxide ions being produced, right? So therefore, one would say that the resulting solution, KF solution, is basic as a result, all right? Which, if you look at the summary that I showed you earlier, potassium fluoride is formed from a strong base and weak acid. This is strong, this is weak. And based on the table I showed you, you would expect that the salt, potassium fluoride, would be acidic, would be basic as a result, plus water, all right? So the resulting solution, you'd expect to be basic, all right? So that's basically how you can make that kind of prediction in terms of whether or not a particular salt will give an acidic or basic or neutral solution when added to water. All right, any questions about this before we move on? Any questions? Any questions? Any questions out there in Zoom? Any questions? Going once?
No.
Going twice? Okay, so let me go back to the PowerPoint. I think there's one more topic we need to cover, and then that will be the end of this chapter. And that has to do with the relationship between the oxidation states of oxides and the type of solutions that they would form when added to water. What you'll find is that non-metallic oxides tend to, not in all cases, they tend to form acidic solutions when added to water. And we have two examples here. Carbon dioxide, when added to water, will give you carbonic acid, which is a weak acid. and dinitrogen pentoxide. Oh, wait, I didn't realize that the bottom part here is cut off. Okay, I'm at the ones I still go to, all right, I'll try to wing it. Let me minimize. Okay, so yeah, this part was cut off here. The reaction between dinitrogen pentoxide and water to give you nitric acid. So these are two examples of non-metallic oxides that when added to water will give an acidic solution. There are other instances where non-metallic oxides will be added to water and they will give you a neutral solution, such as carbon monoxide, that is basically a neutral oxide. Okay, so the next slide talks about now some other definitions of acid. Now we were introduced to the Arrhenius and the Bronsted definition. So just to remind you of the definitions according to Arrhenius and Bronsted, Arrhenius says an acid is a substance which, when added to water, produces hydrogen or hydronium ions in an aqueous solution, right? That's the Arrhenius definition. And then we have the Bronsted definition of an acid, which says that an acid is basically a substance which is a proton donor. And I think I remember saying that the Bronsted definition kind of broadens the definition such that it includes a wider variety of compounds as acids, all right? Then we have what is known as the Lewis acid definition according to Lewis. And Lewis says that an acid is a substance that can accept a pair of electrons. And he went on to say that a Lewis base is a substance that can donate a pair of electrons. And that even broadens the definition some more to include some other substances. So basically what I'm saying here, that there are some substances that would be considered an acid or a base according to Lewis, which would not be the case according to the Bronsted or the Arrhenius definition, all right? And just to give you a couple of examples here, so basically according to Lewis, the H+ ion in this particular reaction would be a Lewis acid, and the hydroxide ion is a Lewis base. And the reason why in this reaction is because the hydrogen ion accepts a pair of protons from the base, so therefore, according to Lewis, the H+ ion would be the Lewis acid, and the hydroxide ion would be the Lewis base. And here's another example. Let's see what happens here. Okay, so here's another example. The reaction between the ammonia molecule and the hydrogen ion. Again, the hydrogen ion, according to Lewis, would be the acid, and the ammonia would be considered to be the base, and the result would be the formation of the ammonium ion, right? And again, that is because the nitrogen is acting as a Lewis base by donating its pair of electrons to the hydrogen ion, which accepts the electron pair, and therefore, according to Lewis, the H+ ion would be an acid, right? Now, here's an example of a reaction which has two species that would be considered, according to Lewis, an acid and base, but according to Bronsted, would not be an acid or base, all right, involved in this reaction, right? And that's because of the difference in the definitions. So in the case of the Bronsted definition, in order for something to be an acid, it would have to give up a proton or a hydrogen ion to something which will accept it, and that would be the base, right? In this particular case, there's no transfer of hydrogen ions from one substance to another. Instead, what you have is the pair of electrons here being donated to the boron, right? And the result will be the formation of this structure right here. There are no transfer of hydrogen ions occurring. Basically, what you have is a donation of a pair of electrons from one species to another to form this bond right here, all right? So according to Lewis, this would be an acid, and this would be a base, but there are no protons that are donated or accepted. So therefore, according to Bronsted, this would not be an acid-base reaction, but according to Lewis, this would be an acid-base type of reaction, all right? Okay, and then the very last slide in this chapter deals with basically one application of things that we have learned so far, the fact that several preparations that are commercially available for the treatment of heartburn, which, by the way, heartburn is a bit of a misnomer because it has nothing to do with your heart, has to do with basically excess acid in your stomach, which refluxes up into your esophagus, right? So basically, these preparations have been put together, and they're all basic in order to neutralize the excess acid, which is hydrochloric acid, which is, by the way, naturally produced by your stomach to aid in digestion of food. So these are just some examples of different types of over-the-counter medications containing basic substances, and these are the active ingredients listed. So one of the reactions, for example, if you're using, let's say, milk of magnesia, which contains magnesium hydroxide, this is the reaction right here, the reaction between magnesium hydroxide and hydrochloric acid to give you magnesium chloride and water. Here's another example. This is what you'll observe happening in the case of the use of Alka-Seltzer. Basically, again, there's another reaction here between the sodium bicarbonate, which is an active ingredient in that medication, and the acid from your stomach to give you these products. So, you know, these are just basically some examples of basic antacid preparations that is used to treat excess acid in your stomach. And that's basically it for this chapter. So, if I remember correctly, assignment number 3 is what you should still be on, and I gave you some questions that you should be able to attempt on your own. I'm sorry, assignment number 4. Assignment number 4. Okay, so if I remember correctly, I gave you up to question number what did I say? Can someone remind me? 14. Yeah, that sounds about right, because 15 says the paper. Okay, I might have to help with question number 16 because this deals with a diprotic acid. Let me see here. 17. Okay, well, let me ask you this. So, have you tried, well, I'm going to assume that you have attempted at least some of these problems. Any questions or any problems that you may have encountered while trying any of these questions I told you about? Any questions? Or any difficulty, something that you need some explanation for?
Not at the moment for me.
I'm sorry?
I said not at the moment for me.
Okay. All right, what I'm going to do is, let me see which one. Let me see here, let me see here, let me see here. Let me see, let me pay attention. I think I'm going to choose the most difficult one I can identify here, which would be This one, number 16. I hope I have enough space to deal with this. Okay, so the question, oh, somebody said something in the chat here. Let's see. Haven't done much. I'll definitely have questions when I sit down and do it. I'm sorry. Okay, no problem. All right, so this question says, ascorbic acid is a diprotic acid. What is the pH of a 0.10 M solution? And what would be the concentration of the conjugate base, the second conjugate base, basically, because they gave you two Ka values here. This is for the first dissociation, that's for the second. So let me turn on my pen function here. Okay, so basically what I'm going to do is, because you don't need this entire formula to actually answer this question, I'm just going to represent this formula by using H2A. H2A, and when it reacts with water, you're going to get H3O plus HA minus, and the Ka1 value for that is 7.9 times 10 to the minus 5. And then for the other dissociation, the HA minus from the first dissociation will react with water to form hydronium ions and A2 minus. And the Ka value for that, which is Ka2, is 1.6 times 10 to the minus 12. All right, so let's see how we can tackle this. The question is asking for the pH. So what I'm going to do is I'm going to rewrite this equation down here and set up an ice table. H2A plus H2O to give concentration, to give hydronium ion plus HA minus. And then I'm going to set up an ice table where the initial concentration of H2A is 0.10. We don't need to concern ourselves with the water. Here you're going to get 0 and 0, right? And then the change here would be minus X, where X represents the amount of H2A that reacted. The change for the hydronium would be plus X, and the change for the A minus would be plus X, right? So that at equilibrium, you're going to have 0.10 minus X. Here you're going to have X, here you're going to have X. So therefore, I'm going to write up here the expression for Ka1 is going to be equal to the concentration of hydronium times the concentration of A minus divided by the concentration of HA. And this would be equal to X squared over 0.10 minus X. And then I'm going to assume, if you remember, in a couple of examples that we looked at, we assume that X is small compared to 0.10, which means that 0.10 minus X is approximately equal to 0.10, right? So that simplifies this equation to become X squared over 0.1, and that will be equal to Ka1. So therefore, X, let me do this down here, X would be equal to the square root of Ka1 times 0.10. This is Ka1, and then I put the number in. So Ka1 is 7.9 times 10 to the minus 5 times 0.1, which works out to the square root of 7.9 times 10 to the minus 6. So let's see what that gives. So 7.9 times 10 to the minus 6, and then I find the square root of that. And according to my calculations, this works out to be equal to 2.81. I'm sorry, 2.826 figs. Let me erase that. Okay, so 2.8 times 10 to the minus 3. All right. And then I'm going to determine the percent dissociation. because we need to see whether or not the assumption we made here is valid, which I think it is, but just to play it safe, let me put it down here. Percent dissociation would be equal to the concentration of hydronium. I'm sorry, folks, I'm in the way.
Is that HA on the bottom?
I'm sorry?
Is that HA?
Yeah. Mhm. Okay. So I'm about to calculate the percent dissociation divided by the initial concentration of HA times 100%. Now remember, the criteria that is normally used is 5%. The percent dissociation has to be less than or equal to 5%. So let's see if that's the case. 2.8 times 10 to the minus 3 m divided by 0.10 m times 100%. And from the look of things, let me do this here. 2.8 times 10 to the minus 3 divided by 0.1 times 100. Do this again. 2.8 times 10 to the minus 3 divided by 0.1 times 100. So according to my calculation, this works out to be 2.8%, which is obviously less than 5%. So therefore, the assumption that we made is valid. So what does that mean? That means that the X that we calculated here is going to be equal to the concentration of H2O plus, which means that the pH will be equal to minus log of 2.8 times 10 to the minus 3. So let me see what that gives. 2.8 times 10 to the minus 3 log. Hold on. 2.8 times 10 to the minus 3 log and then minus. So according to my calculation, this works out to be equal to 2.55. All right. So that would be the answer to this part of the question, what is the pH, right? Now, let me just say this. Now, you might be wondering, okay, we have calculated the concentration of hydronium ion from the first dissociation. What about the second one, right? Because the HA minus here will react with the water to form more hydronium ion. And the answer to that is that, yes, that will happen, but the concentration of hydronium ion that will be produced as a result of the second dissociation would be very, very, very small. So much so that you can ignore it. And the reason why I'm confident in saying that is because we calculated that the percent dissociation for the first dissociation is less than 5%. For the second dissociation, it's going to be even smaller because when you compare the Ka2 value to the Ka1 value, what do we see? This is 7.9 times 10 to the minus 5. That is 1.6 times 10 to the minus 12, right? That is different by a factor of about 10 to the what? 10 to the 7. You see what I'm saying? So the second dissociation will be so small that we can ignore the second dissociation in terms of the amount of hydronium ions that will be produced. Okay, so the answer for the first part is that the pH of the solution will be 2.55. All right? Okay, any questions about this? Any questions? Any questions?
You said concentration is like.
For the second dissociation, the concentration of the hydronium will be so small that you can ignore it. All right? Okay, any questions? Let me see if there's anybody out there. Okay, I guess there are no questions out there in Zoom. Okay, so I'm going to need some more space, obviously, so let me know when it's okay for me to clear this.
I'm okay on Zoom here.
Okay. Can I clear this? All right, let me clear this. And I'm going to need your help because I'm going to need some information which I'm going to erase here. So let me clear this. Now, the next question is, what will be the concentration of the A2 minus, right? So in this case, we're focusing on HA minus reacting with water to form A2 minus plus hydronium, all right? So what I'm going to need your help with, because I'm going to set up another ice table. I'm going to need your help in terms of What was the concentration of hydronium that we calculated previously? That goes here. (2.8 times 10 to the minus 3, right?
Yeah.
And now, in the case of the first association, right, you will see that whatever all right, let me write the first association down here. The first association was this. To give you H0 plus HA minus. Now, in the case of the first association, at equilibrium, if this is a concentration of hydronium, that means that the concentration of A minus is going to be the same because it's a 1-to-1 mole ratio between those two. So that means that the initial concentration of HA minus for the second dissociation is going to be 2.8 times 10 to the minus 3, right? This is going to be 0. The change here is going to be minus X. Here is going to be plus X. Here is going to be plus X. So therefore, you're going to have 2.8 times 10 to the minus, 10 to the minus 3 minus X here. Here you're going to have X, and here you're going to have 2.8 times 10 to the minus 3 plus X. Now, here's the thing. Remember, the percent dissociation for the first dissociation is very small. For the second dissociation, it's going to be even smaller, right? So we can basically assume that this is going to be approximately equal to 2.8 times 10 to the minus 3. And this is going to be approximately 2.8 times 10 to the minus 3, all right? So therefore, when we write down the Ka2 expression, that's going to be equal to concentration of A2 minus times concentration of hydronium divided by concentration of HA minus. This thing is kind of acting up. Okay, so basically we're going to plug these terms, right, into this equation. But the aim is to find A2 minus. So what I'm going to do is rearrange it to get an expression for A2 minus concentration is equal to Ka2 times the concentration of HA divided by concentration of hydronium. And then we put the numbers in. But here's the thing. HA minus and hydronium ion concentrations are the same. So we can simply cancel those two. And therefore, we're going to end up with the concentration of A2 minus being equal to the Ka2 value, which will be equal to 1.6 times 10 to the minus 12 M. And that will be the answer for that part. And no surprise, it's so small because, again, the percent dissociation you would expect the percent dissociation for the second step to be much less compared to the first step. So that's basically how that works. All right. Any questions about this? Any questions? Any questions? Any questions out there in Zoom?
So HA and H3O canceled out because they have the same value, correct?
Exactly. And that's because we made the simplifying assumption that X here is small, X here is small, very small, which it is, because it turns out that X, which is equal to the concentration of A2 minus, is 1.6 times 10 to the minus 12, which is very, very small compared to 2.8 times 10 to the minus 3. So even if we calculate the percent dissociation, you're going to see that it's very small.
Okay.
If you divide, in fact, let me do that right now. If you divide 1.6 times 10 to the minus 12 by 2.8 times 10 to the minus 3 times 100%, I got 5.7 times 10 to the minus 8%, very small, right? So therefore, the assumption that we made for the second dissociation is valid. All right?
Okay.
Okay, any other questions about this one? Any other questions? All right, so what I'm going to do, I'm going to leave you to try the others. And again, as always, please feel free to, let me clear this, to, contact me if you have any issues with any of the questions, and then I'll be able to help you with those, because I want to get to the next chapter, which deals with some more equilibrium situations. We'll be dealing with acid-base equilibria and some other related topics, solubility, equilibrium, and so on. All right. So what time is it? 8:47. Okay, so we should be able to get into this chapter a bit. So first thing we're going to talk about in this section is what is known as the common ion effect. And this is based on what we learned 2 chapters ago with respect to Le Chatelier's principle. So let me just state what the common ion effect is. The common ion effect is basically the shift in equilibrium that is caused by the addition of having an ion in common with the dissolved substance. And you're going to see how Le Chatelier's principle comes into play. So basically, what is happening here is that the presence of a common ion will suppress the dissociation of a weak acid or weak base. And later on, we're going to see in the case of certain ionic compounds, it will suppress the ionization of those compounds as well. But for now, we'll be focusing on weak acids and weak bases. So basically, this is what happens. Now, in this particular example, we're going to look at a mixture of sodium acetate, which is a strong electrolyte, and acetic acid, which is a weak acid, right? So when you add sodium acetate to water, it will dissociate completely, as you can see from this equation. When you add acetic acid to water, it will undergo partial dissociation, right? Now imagine, let's say we had only acetic acid in the water by itself, right? So this will dissociate by itself, no problem. It will be partial dissociation. So therefore, there'll be a small amount of ions present. Then you add all of a sudden the sodium acetate, right, which undergoes complete dissociation. So what that will do is that it will increase the amount of acetate ions present in the solution. So we know what happens according to Le Chatelier's principle. If you all of a sudden increase the concentration of one ion present, then that will result in this equilibrium shifting to the left, all right, as a result of the increase in the concentration of the acetate ion. So what does that mean? That means basically that the percent dissociation of acetic acid will be less because of the equilibrium shift to the left, reducing the concentration of H+ ions and increasing the concentration of the acetic acid molecules, all right? So this is basically what happens in this effect, the common ion effect. The presence of the common ion, in this case, the common ion is the acetate ion. It's going to reduce the level of dissociation or the percent dissociation of the acetic acid. And this will become important later on, as you're going to see, when it comes to how buffers behave, right? You're going to learn about buffer solutions, which are very important solutions, especially when it comes to biological systems, all right? No, you're asking me to remember something from biochemistry, which I haven't done in a long time, because I remember that term.
It's basically like it's by being there, it's like competing with the other substances.
I'll have to think about that. It's a very good question. I have to think about that. When I hear the term competitive and non-competitive inhibition, I think of it in relation to enzymes, right? And it's been a while since I've done biochemistry, but you're talking about an inhibitor competing for the same site on the enzyme molecule as the substrate that it would normally interact with. I'm not sure. I'll have to think about that some more. I'm not sure that would apply in this particular case. It could, but I'm not sure. So what would be the competitors in this case? I don't see it as that. Come to think of it, looking at it right now, I don't see it as that, because it's basically you're just increasing the concentration by adding the sodium acetate to the acetic acid solution. You're basically increasing the concentration of acetate in the mix, and that will force the equilibrium in that way. So I would say no, not quite the same way. Yeah, I wouldn't say it's the same thing. Okay, so let's consider a mixture, kind of similar to what we just looked at. We have a salt, Na, and the weak acid of that salt, which would be like in the case of the example we saw before, acetic acid. So as we said before, the salt would undergo complete dissociation, as you can see here, and the weak acid will undergo partial dissociation, as you can see here, right? So we're going to look at some quantitative aspects. We can write down the Ka expression for the acid, which would be equal to this right here, and we can rearrange it to solve for H+, which would be equal to Ka times the concentration of the acid times the conjugate, divided by the concentration of the conjugate base. And then we can find the minus log of both sides. Why? Because we are interested in finding an expression for the pH of this sort of combination, right? So minus log of H+, which would be the pH, will be equal to minus log of Ka minus log of the concentration of HA over A minus. This part here is going to be equal to the pH. Oh, by the way, another way of rewriting this is that if you flip these two, and you should know this from your previous algebra experience, if you flip the A minus and the HA here, this negative sign becomes a plus sign, right? So, as I was about to say, the minus log H plus here, that would be the pH, and the minus log of Ka, that would be the pKa, all right? And therefore, we're going to end up with this equation here, which you can use to calculate the pH of such a solution. This equation is called the Henderson-Hasselbalch equation, right? And the Henderson-Hasselbalch equation is used to calculate the pH of this solution, which you're going to see on the next slide is called a buffer solution, all right? Another way of expressing it is the pH is equal to pKa plus log of the concentration of the conjugate base divided by the concentration of the weak acid, all right? Okay, so you can use this equation to solve problems such as this one right here. What is the pH of a solution containing 0.30 m formic acid and 0.52 m potassium formate, right? So this is a mixture of a weak acid and the conjugate base, right? So first thing we're going to do is write down an ice table. We start off with the equation for the dissociation of the weak acid. Initially, you're going to have, and this is very important and kind of different from the previous ice tables that we had before. Initially, the concentration of the weak acid is going to be 0.30, and the concentration of the conjugate base, which is formed from the potassium formate, is going to be 0.52, right? The initial concentration of the H+ will be 0 initially, all right? Then we look at the change. As far as the formic acid is concerned, some of it will react, so the change for that would be minus X. The change for the H+ would be plus X, and the change for the conjugate base would be plus X. So that at equilibrium, we have these terms right here, all right? And then we plug these into the, we make an assumption that X is so small that 0.30 minus X is 0.30, and we do a similar thing for this part here. 0.52 plus X is approximately equal to 0.52, and then we plug those values into the Henderson-Hasselbalch equation. Of course, you're going to need a pKa, so that would have to be provided to you. Remember, there's a table that I showed you in Canvas. You will have access to that table in your test, right? That table gives you a list of Ka values for weak acids and Kb values for weak bases, right? So all you have to do is consult the table, and you look up the Ka value for the formic acid. You find the minus log of that. That's equal to 3.77. That goes here. And then you plug in the other values into the equation, as you can see here. And according to this, this works out to be equal to 4.01, all right? So that's basically how you use the Henderson-Hasselbalch equation to calculate the pH of such a solution of a weak acid and its conjugate base, all right? Okay, any questions about this particular example? Any questions? Any questions out there in Zoom? Any questions? Okay, next slide. Okay, so now we're going to get to the definition of a buffer solution. What we were talking about, the examples that we looked at in the previous 2 or 3 slides, those are all examples of buffer solutions. So let me give you the definition of a buffer solution. A buffer solution is a solution made up of a combination of a weak acid or a weak base and the corresponding salt of the weak acid or the weak base, right? So if you're starting with a weak acid, then you're adding a salt of that weak acid to the solution. That's a buffer solution. Or if you have a weak base in combination with the salt of that weak base, that would be also a buffer solution, right? Both must be present. If you have one without the other, then you're not dealing with a buffer solution. So if you have a weak acid, it must be combined with a weak base. I'm sorry, it must be combined with the salt of that acid. All right. If you're starting off with a weak base, then you must have, in addition to that, the salt of that weak base. All right. So the unique thing about buffer solution, and the reason why it's very important, is that these solutions have this unique ability of resisting changes in pH when you add a small amount of acid or base to it, right? This is very unique because pretty much all other solutions don't behave that way, or even pure water. In fact, pure water, certainly doesn't behave that way, right? All other solutions, if you add a small amount of acid or base to it, the pH is either going to increase or decrease drastically, all right? And you're going to see, I think I have a graph here, or maybe it's on the next page, right? Where you're going to see how that happens, right? But a buffer solution, if you add a small amount of acid or base to it, the pH does not change by much, right? So it says here, consider an equal molar mixture of both sodium acetate and acetic acid. And if you add a strong acid to it, now we're going to get into a description as to how it basically resists changes in pH. If you add a strong acid to it, the acid is going to react with the basic part of the buffer, according to this equation, right? So what's going to happen is that the acetate ion, which is the conjugate base, will react with the H+ to form acetic acid. So basically what's going to happen is that the acid that you add to it, the acetate ion is going to remove most of it to form the acetic acid molecule. So therefore, the concentration of H+ in the end will not change that much, all right? If you add a strong base, what will happen is that the hydroxide ion is going to react with the acid part of the buffer and therefore reduce the concentration of the OH-, and therefore the pH again will not change by much. And please note, in both cases, you're forming, in this case, a weak acid, in this case, a weak base. So therefore, the weak acid and weak base that is formed in each case will not have a profound effect on the pH, and therefore the pH will change, but ever so slightly, all right? So that's basically a description as to how a buffer works. And we're going to see, maybe not today, but we're going to see an actual mathematical or quantitative example of this, all right? So this is the graph I was alluding to. It shows you the pH of both a buffer solution and pure water as you add acid to it, right? And you'll notice in the case of water, if you add acid to it, the pH changes drastically from 7 to, when you add 0.02 moles of acid to just under 2, and then it continues to decrease as you add more and more acid. In the case of a buffer solution, the pH does change, it does decrease, but as you can see, the decrease is very slight, all right? So that's the difference between buffer solutions and other solutions and pure water. The pH will change when you add a small amount of acid or base to it, but it does not change by much. And this is important in biological systems, as I'm quite sure you may have, encountered in your biology courses. There are certain processes, biological processes that require the environment to be within a certain pH range, right? And there are certain buffers that exist. There are certain combinations of different substances that make up a buffer in biological systems, which basically maintains a pH range so that those processes can occur without any issues whatsoever, all right? So that's the importance of pH, of buffers when it comes to biological systems, all right? Okay, so let's look at this example. Now, let me remind you of what a buffer mixture is. It's either a weak acid and the salt of that weak acid, or a weak base in combination with the salt of that weak base. Because this question is asking, which of the following are buffer systems, right? And it gives you some combinations here, right? So let's look at the first one. A, potassium fluoride and hydrofluoric acid. Would that be a buffer solution? The first thing let me give you a hint. The first thing I would ask myself is whether or not the acid is a strong or weak acid. And again, you need to remember those 6 strong acids. I would ask you what those 6 strong acids are, but I don't want to embarrass you all. It's a weak acid, right? So we have HF, which is a weak acid in combination with the salt, potassium fluoride of that weak acid. So therefore, in the case of A, that's a buffer solution, right? Okay, what about B? Combination of potassium bromide and hydrobromic acid. Would you consider that to be a weak acid? I'm sorry.
No.
Would you consider that to be a buffer solution?
No.
No, because
HBr is a strong acid.
exactly, HBr is a strong acid, so therefore it's not a buffer solution. Okay, what about the last one? Now, the last one is a bit tricky, but it's the same principle that applies. Sodium carbonate in combination with sodium bicarbonate.
I want to say yes.
Okay, why? Because, which is correct, by the way, you're right, but I want to hear the rationale.
It looks like NaHCO3 is a conjugate acid.
Well, it is a conjugate acid
That
of
would mean
the carbonate ion, right?
yeah, that would mean it's a weak base.
Well, that's where you're kind of wrong, because what happens, okay, the key to understanding this one here, write this down, is that you could look at it as a carbonate ion here by itself and the bicarbonate ion by itself, right? This here would act as a weak acid, and this would be the conjugate base of that weak acid. So yes, it would be a buffer, but that's the reason why, because it's a combination of a weak acid, and this would be the conjugate base of that weak acid. So the answer is, it's a buffer solution, all right? Okay. Any questions about that particular example? Any questions? Any questions? No questions? Okay. Now this one is going to take some time, which I don't think I'll have. So I think I'm going to stop here for today, because this is going to, I don't want to start this question and then stop in the middle of it, all right? Oh, yes, sir. All right, so we're going to stop here for today. Let me get those of you who came in late into my record book here. Okay, let's see here. Is okay, Chesmore is here. Gonzalez Albo, I don't see her. Labrador, I don't see that name. Papa is here. And Simpson, I don't see that name. Okay. All right, so that's it, folks. So I see you guys on Wednesday, all right?
Oh,
Yes, sir. You have a question?
somebody's asking something in chat.
Oh, really? Let me see. How do we submit the redo? Oh, I thought didn't I create a Dropbox? I thought I did. If I haven't, let me take care of that now. Let me see here.
In this announcement, you put the dates as 4/20 instead of 2/20.
Oh, it should be 2/20. Okay, thank you for letting me know that. Yeah, that would be too far ahead, a deadline. Okay, so let me take care of the Dropbox if I have not done so already. Let me go here. Let me go here. No, not there. I should go to assignments. That's where I need to go. Okay, assignments. And yeah, it looks like I did actually created a Dropbox. I did not put a deadline date on it, so let me do that now. Let me just go here, just to make sure it's set up properly. Oh, okay, I see the problem. I didn't do an extra step. Okay, so now the Dropbox should be available. All right. Okay, so if there are no other questions, folks, I'm signing off. And I'll see you guys on Monday.
Yep. Have a good one.
You too.